Hello, everyone, and welcome to our last virtual week of this quarter. So before I get started with the math, I just had a couple of announcements, or really just one announcement, which is that I posted some information about the final exam on Canvas, so please go and read that. Basically, I will be uploading a PDF that has the final exam during the final period. So you need to be available to work on the final exam during our final exam period, which for this class is Monday, I believe it's March 20, let me think. So tomorrow is the 16th, so it's the 23rd. Monday, March 23rd, between 10:30 a.m. and 12:30 p.m. So basically I'll upload a PDF of the exam just before 10:30, and then it'll be like a 2-hour exam, but then I'll give you an extra half hour at the end to take pictures of your work and your answers and upload those to Canvas. So please go look at the description. If you look on the modules section on Canvas, you'll see a file or an assignment called Final Exam, and it really lays out, what I expect for you to upload and all of that. I also put a assignment that's called Practice Uploading Files. So if you want to make sure that you know how to upload files so that when you are kind of in crunch time during the test, you don't have to worry about it, you can use that to just kind of practice, see what it looks like to upload things. Other thing, so I will get the final review posted as soon as I can. It always takes me a while to come up with the final review just because it's hard to come up with good questions. So I'm working on that, and I'll get that up as soon as I can. And I guess one other thing. So my plan is for this week. So Monday through Thursday, I'll make kind of typical videos like we've been doing. And then for Friday, I think what I'm planning to do is take requests for problems from the review for me to make a video where I go over those. Obviously I don't have time to go over the entire review, but so I'll post the review as soon as I can, and then I'll probably post some kind of like a survey or something like that you can just tell me which problems you most would like to see a video of me going over. So yeah, I'll let you know when that stuff is up and running, and just wanted to kind of give you a heads up. Okay, so let's get into some linear algebra. So I want to give you a warm-up problem to try to remind you what we were working on last time, and then it will also bring us into just something that we didn't quite get to in the last video. So what I would like you to do is let A be this following matrix. So 4, -1, 2, 2, 1, 4, 3, -3, 9. So what I would like you to do is to determine whether lambda equals 3 is an eigenvalue of A, and if it is, find one specific example of an eigenvector. So I would recommend pausing this, trying to see if you remember what that process is. This was basically what we were working on last week at the end of the week, but then we'll go over it again together because there's a couple things I want to point out along the way. Okay, so just to remind you the definition of an eigenvalue and an eigenvector, as well as kind of the general process. So remember that the definition was that a vector, so a non-zero vector, X, is called an eigenvector of an n by n matrix A. So we're only doing this with square matrices. If A times that vector is equal to a number lambda times that vector for some scalar, and so lambda is this Greek letter, and so this number, this scalar, is what's called the eigenvalue that goes with that eigenvector. So the way that we actually work with this definition is, instead of writing it as a times x is equal to lambda times x, we saw last time that you can rearrange this to be ax minus lambda x is equal to the 0 vector, and then you can rearrange that as a minus lambda times the identity times x is equal to the 0 vector. So if you want to be refreshed on what was the exact kind of algebra to go from that starting equation that I wrote down to this bottom equation, you can look in the last video for that. But the last thing that I wrote here, this one that I will circle now, this is basically this is like our working kind of approach for finding eigenvectors given a particular eigenvalue. So this is the one that you want to kind of go to. So basically, with this thing that I just boxed in green, two things. One is a vector x is an eigenvector if it is a non-trivial solution, right? So because x is not allowed to be the 0 vector. 0 vector does not count as an eigenvector. So any other vector that is a non-trivial solution to the thing boxed in green is considered an eigenvector. And then if you're trying to figure out in general whether a number lambda is an eigenvalue, basically lambda is an eigenvalue. And I probably should have reversed the order that I'm writing these two lines, because I think it makes a little bit more sense if I write them in the other order, but that's okay. So lambda is an eigenvalue if basically that same equation, a minus lambda I times x equals 0, has a non-trivial solution. So if you're trying to figure out whether something is an eigenvalue, you're basically just trying to figure out, does it have a non-trivial solution when I do a minus lambda times the identity times x is equal to 0, and then whatever those solutions are that you find, those are the eigenvectors. So let's look at this specific example. So we're trying to figure out whether lambda equals 3 is an eigenvalue. So what we want to do is we want to do our matrix A, we want to subtract 3 times the identity from that matrix, and then basically solve that matrix times x is equal to 0. So let me scroll down a little bit. So in this case, we have a minus 3 times the identity. So that's going to be 4. I'm going to write the original matrix down just to be thorough here. 2, 1, 4, 3, negative 3, 9. And then we're subtracting from that 3 times the identity, which means that we're subtracting 3 basically just from the diagonal entries while leaving everything else the same. Oops. That should have been a 3. Okay. And so when we do that, we get 1, and then the rest of that first row stays the same, and then negative 1, then we have negative 2, and then negative 3, and then the last row we have 2, 4, and we're subtracting 3 from that, so we get 6. So now we're trying to figure out what are the solutions to, so we want to solve this matrix that we just found, 1, 2, 3, negative 1, negative 2, negative 3, 2, 4, 6, times x1, x2, x3, because that's the vector x we're trying to find, right? And we want to get all zeros. And so if this has a solution that is not the trivial solution, that means that yes, that 3 was an eigenvalue. So if we were to try to do this and we were to find, oh wait, this only has the trivial solution, that would tell us that 3 was not an eigenvalue. And And then if we do find our non-trivial solutions, those will be the eigenvectors. So in this case, or in most of these cases, the easiest thing is to make an augmented matrix and kind of see where that goes. In this case, you can probably see where it goes, but I'm going to write it all down anyway. So what you probably notice here is that all of the second and third row can both be expressed as multiples of the first row, right? So for example, if we wanted to solve this, we could add one copy of the first row to the second row, and we could subtract 2 copies of the first row from the bottom row, and that would give us 1, 2, 3, 0, 0, 0, 0, 0, 0, 0, 0, 0. Okay, so where do we go from here? Basically, you want to think of this as, reinterpret this as what it tells you about your system of equations, and then we're going to put it into parametric vector form. So we have x1 is equal to negative 2 x2 minus x3. Oops, I don't know why I wrote a 3 there. Or no, that is right. I said the wrong thing out loud, but I wrote the right thing. Minus 3x3. And then x2 and x3 are both free variables, right? Because those are not pivot columns. And so if we keep going with this, we find that our solution vector can be written as negative 2x2 minus 3x3 x2, x3, and then we split that up in the same way that we always do with this parametric vector form. So we can pull out an x2, and we get negative 2, 1, 0, and then we have x3 times negative 3, 0, 1. Okay, so what is this telling us? This is telling us, so first of all, we already confirmed that 3 is in fact an eigenvalue. So this now tells us that any eigenvector corresponding to 3 is going to be a linear combination of the vectors negative 2, 1, 0 and negative 3, 0, 1, right? Because what we have written down right now, x2 and x3 can be any number. So this is going to be another way of writing what we have right now is that it's the span of these 2 vectors. So anything that you pick that is in the span of these 2 vectors, so you can pick any numbers you want for x2 and x3, and anything you pick is actually going to work. It's going to be an eigenvector corresponding to the eigenvalue of 3. So for example, if we wanted one specific solution, we could actually just pick either one of those 2 vectors, right? Because that would be like 1 times one vector plus 0 times the other vector. If you want to get more interesting, we could like maybe add them together. So, one example of a solution would be negative 5, 1, 1. And so we can check that. And I think it's kind of nice to check it because it almost feels magical, at least to me. But maybe I have low standards for what I consider magical. 3. So I'm going back, remember, to the original matrix, right? So the matrix we were working with earlier was the original matrix minus lambda times the identity. Now we just want to go back to our original matrix, and we're just confirming that when we plug in this vector and multiply, that we actually just get a multiple of the vector negative 5, 1, 1. So if we do this, in the first entry we'll have negative 20 plus 2 plus 3, so that's negative 15. In the second entry we'll have 5 plus 1 is 6 minus 3 is 3. And then the third component will have negative 10 plus 4 is negative 6 plus 9 is 3. And it worked. That is the same thing as 3 times our original vector. And that shows us that we were right, that this is in fact a eigenvector. Okay, so the thing I want to point out here that kind of just brings in like one other piece of language, basically. So we know that all eigenvectors can be described as the span of these two vectors. So the span of these two vectors is a subspace of R3, right? Because if you take any set of vectors in R3 or Rn in general and take their span, it's always going to give you some kind of a subspace. So this span here, and let me use another color and go up here, and then I'll write something more generally in a moment. So this set, the span of these two vectors, this is what is called an eigenspace. So it's an eigenspace of the matrix A corresponding to lambda is equal to 3, because that was the eigenvalue that it came from. And basically it's just a subspace of R3. And there's not really, this isn't anything particularly deep. Again, it's just that anytime you have a span of some vectors, it is a subspace, it's a vector space. So in this case, it would be a plane, right, in R3, the span of these two vectors. And so what this is saying is that any vector that is an eigenvector of this matrix corresponding to an eigenvalue of 3 is going to lie on this plane. And by the way, these two vectors, so we talked about this a little bit when we were talking about null space, because this actually is a null space, and I'll get to that in a second. But automatically, the system that we use is going to guarantee that the vectors we found are linearly independent. So not only can we say that the span of these vectors is equal to the eigenspace, but actually the two vectors themselves, so this set here, this is going to be a basis for the eigenspace. So the span is the whole vector space, the whole subspace, the eigenspace. The set of vectors specifically is a basis for that eigenspace. So let me just write something down that's a little bit more general than that. So in general, actually, I think that's probably enough space. In general, if A is an n by n matrix, the set of all eigenvectors corresponding to a specific eigenvalue, because remember, one matrix can have multiple eigenvalues, and we'll see that actually later today. So the set of all eigenvectors corresponding to an eigenvalue and eigenvalue lambda is always going to be a subspace of Rn, and it's called an eigenspace. I know it's kind of a fancy sounding word, but really we're not saying anything too new here. I don't want you to think that this is some crazy new concept, just saying that's a subspace of Rn. And the reason I'm saying that's not really a new concept is because it actually, so we already knew that the thing that we're talking about here is a subspace, because let's go back to where this all came from. So looking at the equation that's boxed in green here, when you're trying to find eigenvectors, you're essentially finding the null space of a matrix, right? We're finding the null space not of A, but of A minus lambda I. So going back to this line here where it says solve, so by setting up this matrix and then solving, we were finding the null space of A minus 3i. So I'm just going to write that down below here. It's not just the eigenspace of A. We could also think of it as the null space of the matrix that you get by doing A minus lambda I. Okay, so there's one more thing I want to talk about before we get to some new stuff. So this is something that came up on the worksheet. So I think it was like the last problem I put on the worksheet, and I asked you basically to think about what it means for 0 to be an eigenvalue of a matrix A. So I'll say it this way. What does it tell you about a matrix A if 0 is an eigenvalue? So first thing, and I wrote this out on the worksheet on the solutions, but I just want to say it out loud. I know that like we're not allowed to have 0 as an eigenvector, and I just don't want you to mix those two concepts up. So I'm going to write that first. So this is not the same as saying 0 is an eigenvector. So if 0 would be an eigenvector, so remember, we're not allowed to consider the 0 vector an eigenvector. Basically what that would mean would be that a matrix A times the 0 vector is equal to lambda times the 0 vector. The problem with that, and the reason that we don't allow there to be 0 eigenvectors, is that is always going to be true, right? If you take a matrix A and you multiply it by the 0 vector, you're going to get the 0 vector. And any number times the 0 vector is also the 0 vector. So that just like isn't interesting. When we're looking for eigenvectors, we're looking for things that are specific to that specific matrix. And so saying that this equation that I've written here is true for the 0 vector just isn't really telling you anything about the matrix, because it's always true. So in general, when we say eigenvector, we always mean non-zero vectors. This is different though. So what is this saying? So if 0 is an eigenvalue, that means, so if 0 is an eigenvalue of A, that means that there are non-zero vectors x such that A times x is equal to 0 times x. So what do you get when you take 0 and multiply it by any vector? You get 0. So it's basically telling us, so if 0 is an eigenvalue, that's telling you that there's a non-zero vector x that when you multiply it by A, you get the 0 vector. And what does that tell us? That tells us that A is not invertible, right? As soon as you have non-trivial solutions, so when we say trivial solutions, we mean the 0 vector, right? So of course, Ax equals 0 has the solution that x is the 0 vector. But specifically, when we're talking about eigenvectors, we're talking about non-zero vectors. So if there's a non-zero vector that makes this equation true, that means that A is not invertible. So let me write that down another way. So I said there are non-zero vectors x such that Ax is equal to 0, i.e. there are non-trivial solutions to Ax equals 0. And we know what that means. We've seen that idea come up before. That means that the matrix is not invertible. So basically, if a matrix has 0 as one of its eigenvalues, that tells you that, so what, I mean, let's think about it a different way. If it has 0 as an eigenvalue, that means that there are vectors that when you multiply by A, that whole vector gets scaled by 0, meaning that just goes straight to 0. And so that should already show you that it's not, how do I say this? That if it's a linear transformation, it's not 1-to-1. And so that would also be another way of seeing that's not invertible. So basically we have something new to add to the invertible matrix theorem now. So what can we add to the invertible matrix theorem? That in order for an n by n matrix A to be invertible, it cannot have a 0 eigenvalue. So let me just write that below here. So we can add to the invertible matrix theorem, A does not have 0 as an eigenvalue. And by the way, when I first uploaded the solutions to this worksheet, I typed the wrong thing, and almost everything I wrote was correct, but for some reason when I wrote this last part, I said A does have 0 as an eigenvalue. So make sure if you downloaded the worksheet from Friday, like very quickly after it was uploaded, you probably have the version that has it written wrong. So you might want to download the new version. Okay, so we are now ready to get into a little bit of new stuff. So far when we've talked about eigenvalues and eigenvectors, I've always kind of handed you an eigenvalue or an eigenvector, right? So we did examples where it's like, here's an eigenvector, find the eigenvalue, or here's an eigenvalue, find the eigenvectors. And so now we're going to learn how you can kind of start from scratch and just figure out what the eigenvalues are without having to be handed them. And so this is something we're going to spend a couple of days on. So we'll start today and we'll do just some 2x2 matrix examples, and then we'll get into the next, tomorrow's video, we'll get into doing some bigger examples. Okay, so this is section 5.2 in your book, and it's called the characteristic equation. Okay, so I want to go back to something that we already had written down, what I had written in that green box earlier. So we have this nice equation, a minus lambda I times x is equal to 0. So one of the things I had written down is that lambda is an eigenvalue of that matrix A if there is a non-zero vector x satisfying the equation. So this is going to feel almost like what we were talking about actually on the last slide, but in the last slide we were talking about having the matrix A times x equaling to 0. Now we're talking about having A minus lambda I times x being equal to 0. So we're about to write down some things that you might feel like we just did the same thing, but it's important to realize that we're now talking about slightly different equations. So on the last slide, maybe let me just go back to it for a second. On the last slide, we were specifically talking about the case where you have 0 as an eigenvalue. And when you have 0 as an eigenvalue, that leads you to having A times x is equal to 0. Now we're talking generally about finding any eigenvalue. You're always going to start by kind of setting it up like this. A minus lambda I times x is equal to 0. Okay, so lambda is going to be an eigenvalue if there's a non-zero vector that satisfies this equation. So as we said earlier, that basically means that there is a non-trivial solution to this equation, and that suggests that this matrix A minus lambda I is not invertible. Right? So let me write some of those ideas down. So if there's a non-zero vector x satisfying the equation A minus lambda I x is equal to 0, that's the same thing as saying that, this is going to be like, I'm basically just rewriting the last line using slightly different language. Another way of saying that is A minus lambda I times x equals 0 has a non-trivial solution, a non-zero solution. But we know that if you have a matrix times a vector equaling 0 and that has a non-trivial solution, that means that that matrix is not invertible. So in this case, that means the matrix A minus lambda I is not, sorry, I have to do that, not invertible. And what do we know about matrices that are not invertible? Well, actually a whole lot of things, right, because of the invertible matrix theorem. But specifically, one thing that we know is that if a matrix is not invertible, its determinant is equal to 0. So that's the part that we're going to focus in on here, is this fact that if lambda is an eigenvalue of a matrix A, that's always going to mean that the determinant of A minus lambda I is going to equal 0. And so we can basically use this fact to find eigenvalues. So I'm going to write down kind of a general fact here. So in general, and actually, let's do actually a specific example first, and then I'll write kind of the general thing. I think it would just feel more meaningful if we do the example first. Okay, so let's let A equal a 2 by 2 matrix, 2, 3, 3, negative 6, and we're basically going to find all eigenvalues. So how are we going to do this? We're going to basically use the thing that's boxed in pink above. We know that lambda is going to be an eigenvalue, so lambda is an eigenvalue if and only if the determinant of A minus lambda I is equal to 0. So we want to set up a matrix that we'll see that it will end up having lambdas in it, and then we'll find the determinant of that matrix and set it equal to 0. So A minus lambda I is going to look like this. We'll have our original matrix, 2, 3, 3, negative 6, and then we're going to subtract lambda times the identity would give us a matrix where we have lambdas on the diagonal. And so when we do that subtraction, we get 2 minus lambda, 3, 3, and negative 6 minus lambda. So now what do we want to do? We want to take the determinant of this matrix and set it equal to 0, because that will tell us, that will allow us to then solve for what that original eigenvalue lambda should have been. So the determinant of A minus lambda I is going to be the determinant of 2 minus lambda, 3, 3, negative 6 minus lambda. And luckily we're dealing with a 2 by 2, and we know that there's an easy formula for finding the determinant. It's just going to be the kind of diagonal entries minus the other 2 diagonal entries. So, the product of the diagonal entries minus the product of the other 2 diagonal entries. So we have 2 minus lambda times negative 6 minus lambda, and then from that we're going to subtract 3 times 3, which is 9. So if we multiply this all out, we're going to get, actually let me write it here. So if we multiply this all out, we're going to get negative 12 minus 2 lambda plus 6 lambda plus lambda squared minus 9. Let me just check that with my work to make sure that's right. Yes. And so if we simplify that, we get, let's see, negative 21. Actually, let me write this in a different order. Lambda squared plus 4 lambda minus 21. So this thing that we just found, we haven't finished this problem off yet, but this is what's called the characteristic polynomial of the matrix A. So it's a polynomial where the variable is lambda, and notice that the degree of this polynomial is 2. And we'll see that that's because it's a 2 by 2 matrix. So once you have the characteristic polynomial, then you can set that equal to 0, because we want the determinant to equal 0. So we can say lambda squared plus 4 lambda minus 21 is equal to 0. And then this factor. So we can do x, x minus, or x plus 7, and x minus 3, sorry, is equal to 0, not x lambda. And so this tells us that lambda is equal to -7, and lambda is equal to 3. So those are our two eigenvalues. And sometimes you'll label them like lambda 1, lambda 2. But it doesn't really matter too much. So by the way, so the thing, like the polynomial that we got that I circled in turquoise, that's called the characteristic polynomial. When you actually set it equal to 0, then it's an equation, right? It's not an equation when it's just an expression, but now that you have it set equal to 0, now this is what's called the characteristic equation. So not a super important differentiation here, but you just might see both of those words. And characteristic equation is like setting equal to 0. Polynomial just refers to the actual determinant part of it. Okay, so to summarize here what we did and what is kind of like the general case. So in general, lambda is an eigenvalue of a matrix A if the determinant of A minus lambda I is equal to 0. So that's basically what we just did above. So like I wrote up there, I'll just say it here again. This whole thing here is what's called the characteristic equation. So basically you're trying to find a value of lambda that satisfies the characteristic equation. You're solving the characteristic equation. Maybe I'll even write that down. So actually I'll write it in a second. So one more thing I just want to write here is that the part of this that's just the determinant. So the determinant of A minus lambda I is a polynomial in lambda. So when we say polynomial in lambda, that just means that like lambda's the variable instead of x or y or something else. So it's polynomial in lambda with degree n. So the degree is always going to be equal to the size of the matrix. So maybe I should add that in here. So we're talking about an n by n matrix. So this determinant will give you a polynomial in lambda with degree n, and that's called the characteristic polynomial. Okay. So basically, just to kind of summarize what's the approach to find eigenvalues. You want to solve the characteristic equation determinant of A minus lambda I is equal to 0. You want to set up that equation and then solve it for lambda. So today we did an example that was a 2 by 2. And in that case, the determinant is easy to take, right? We know how to just kind of do a special formula that only works for 2 by 2 matrices. So tomorrow we'll do some examples with 3 by 3s, but one thing, if you're trying to kind of get ahead on your homework that I would just suggest is you're probably going to want to use cofactor expansion to find the determinant rather than using row operations. And the reason is that, like, if you're trying to find the determinant of something that is of the form A minus lambda I, it's going to have a bunch of lambdas in it, right? So doing row operations is going to kind of make your life a little bit harder because you're not just going to be adding numbers to each other, you're also going to have this variable lambda added in there. So that's just kind of a quick tip, but we will get into some more examples of that in tomorrow's lecture. All right, so you will see, again, a worksheet posted with just a little bit of practice for what we did and talked about today, and I will see you again tomorrow.